we have a beam, and this beam has a cross section as I showed it here, like any cross section. It doesn't have to be a rectangular, it can be any shape, any shape. Like I draw this one here, but it can be anything. So, and let's say this beam is under a bending, like pure bending, and that bending is M, any number, right? As a result, this beam is gonna bend like this shape, and we just exaggerate here. It's gonna becomes a curvature shape like this one. And we know the top portion is gonna be under compression, and the bottom layer is gonna be under tension. So we discussed, like last lecture, as we move from the top layer, like to the next layer underneath of it, and next layer and next layer, this compression becomes smaller and smaller because we are moving from the top layer, right? The tension the same. You can, it is intuitive, you can feel that the last layer at the bottom is under the maximum tension, because look at the length of this layer, it becomes like stretch a lot. And then the next layer after, above that, less tension, and so on. So somewhere when we go from the top to the bottom, we switch from compression to tension. If we are switching from compression to tension, it means that somewhere in the middle, there must be a layer. And when I'm saying a layer, by the way, pay attention, like this is our beam, right? This is our beam. A layer is the whole area like this plane, all right? So like the whole layer on this beam. But here for simplicity, we show a 2D image. It's gonna be a plane that it is neither under tension nor compression. And that's this layer. So no compression and no tension. All right. This layer, we call it a neutral layer. Or neutral plane. All right. Remember, it's a plane, the whole area. It's not just a line. For simplicity, for 2D, we show it as that. And if we look at the cross section of this beam, so this is the cross section. On the cross section, this layer is going to be like a line that we can see it over here, which I show it by Z, and it is called neutral axis. Or from now on, we just show it by NA, neutral axis, all right? So, because it's important to understand it well, let me try to draw the 3D images of that things. Let's say this is the beam that we have. Maybe a little bit better over there. Okay, let's say just a portion of this beam. And then the rest goes wherever. Okay, so that's the beam, and the cross section we are talking about is like this cross section, all right? It's a plane, yeah, right? That's the cross section. And the way we show the axis, by the way, always we follow the right-hand rules, which I'll explain in a minute. So this guy coming out of this plane is going to be X, and this one over here is going to be Y, and this one is Z axis. So this is X, this is Y, and this is Z axis. No matter how we name them, maybe somebody try to name it differently, but it's common always for a beam, like along the length of the beam, the longitudinal, we call it X, Y is like a vertical axis, and then Z, remember always, we follow the right-hand rules. If you forget the right-hand rules, it's something like this. Let me bring a picture for you guys. So always, no matter how you pick the X, Y, and Z, they have to follow these, like the middle finger, the thumb, and the point finger, right? So, like for example, here it is wrong to have the Z-axis like that. That's wrong. It doesn't follow the right-hand rules, right? So be careful about it. Let's return it back. All right, so this is how we then decide for the axis. X coming out of the cross section, Y is the vertical, and Z as we show it like that one. And this guy is the neutral axis, like the Z axis over here is our neutral axis, right? So this is the NA, neutral axis. Neutral axis, then it's on the cross section. I've seen a student makes a lot of mistake. They confuse this axis with the x-axis along the beam. No, this is not the neutral axis. Neutral axis is on the cross section. And again, as we said, the top layer is under tension, under compression, like this one. Here is under compression. And the bottom is under tension. And graphically, people show it to something like this. If you look at the 2D or the side view of that one, that cross section, it is something which I will try to draw it for you. So the top layer is under tension, compression, something like that. Maybe a little bit smaller. Yep. And the bottom is under basically tension. So that's going to be the tension. They may the values might be different. We don't know. And as we said, as we move from the basically the top to the bottom, the tension and compression switch sign, and somehow in the middle it becomes 0 basically. So let me draw this one. So it becomes smaller, and somehow it becomes like 0. So the compression becomes smaller, the next layer is smaller, smaller, until it becomes 0. And then we switch to tension, small tension, bigger tension, and it gets very, very large tension, right? That's a diagram for stress that we show. Stress diagram. And maybe in other textbook or maybe in assignment or somewhere else, you see a different version of this, which also you should be familiar. It's something like, that's the same. I'll try to draw that one for you as well. If that's the 2D view, it is more like this one. It's basically the same, except the way that people show it. So that's basically the compression. And then around here, we have the tension, all right? So this is the compression side. And this is the tension side, all right? So that's the stress diagram. No matter how we show it, either the first one or the second one. The second one is also common. And this is how stress is changing. So as you can realize then, we can say the top layer has the maximum stress, maximum compression, and the bottom has the maximum tension. And it depends, remember, to how we bend something, right? If I change the direction of M, maybe positive or negative, then these things change, right? For this shape, it's the compression is at the top, tension is at the bottom. All right, so far is easy, it's clear, we know what we are looking. Now let's formulate it. And like always in Mech 260, we don't study the proof of the formula, we use them, but all the proof are very, very simple and they are available in your textbook if you want to study further and study the formula. The formula that we study is simply sigma, like this stress. I'm going to write it down here, is my divided by I. And if we want to get the sign right, we should put a negative there, negative sign there. But most of the time, people don't put that negative sign there because it's intuitive. You can immediately realize, depends on how a beam is bending, if it is under tension or compression. Because remember, sometimes in question, we are asked to sort of indicate if a portion of the beam is under tension or compression, right? We can use this formula Y, and we know Y from O, if you go to the top, it's going to be positive, right? And then below O on this cross section is going to be negative. Negative multiplied by this minus sign is going to be positive, which gives us the sign, the correct sign for tension, right? So that's the main formula that we are going to use in this chapter. Only one formula, and that's the one, this one. So I already, you are familiar with I, which is called moment of inertia, right? But you may say, well, moment of inertia always was about an axis. Here, the axis is about the neutral axis. So moment of inertia, I'm going to write it down here, always about neutral axis, right? So now you may say, well, where is the neutral axis? Well, it can be proved that the neutral axis passes the centroid of the cross section. And this is a good thing. And again, it becomes very simple because the Euler theory, and using the Euler theory, we can simply find the neutral axis. How? Just find the centroid of a cross section. You know how to find the cross section. That's good. So you know where the neutral axis is. If you know where the neutral axis is, it means you can find I. M is given, is the bending for the beam, and Y is the distance, right? Which on this shape I show Y is the distance from each layer that you want to calculate the stresses to neutral axis. But like 99% of the time, we are interested in the maximum stress, right? If you are interested in the maximum stress, this Y then is either this C, like here, or like this distance, let's call it C1. All right. So we can calculate then the maximum compression and the maximum tension, and between these two stresses, the one is bigger is the maximum stress for the beam, which we can base our design based on the maximum of these two maximum compression and maximum tension, right? So I'm going to solve one example here so you see how we can put together all these things. But again, I emphasize a lot on this introductory part, and please do not if you have a question, don't be shy and ask your question. Is there any question? Okay, silent. I assume it's clear, or if it's not, let's move on to solving one example together. So I'll let you guys to read this example and think about it for 30 seconds. I'll do the same. And then we solve it together and see how we can calculate the bending stress in this beam. All right, so let's see. We have a beam, 4 meters. That's a long beam. It looks like a wooden beam. And we want to calculate the stresses at ABC, like on the cross section, ABC. And we just set a point, but of course, when we calculate the stress, it's going to be for the whole layer, right? This A is going to be for the whole layer on top of the beam, and then for layer B, and then for layer C, right? It's not just going to be for one point on the cross section. But where we want to calculate the stress, the question asks us to find the stress in the middle of the beam. Maybe for some reason, this beam broke in the middle, and we are interested in finding the stress in, like, at the middle of the beam, right? At the middle of the beam, like here, around this line. Okay, somewhere here. But for the cross section at point A, B, and C. So here is what we need to do. First, we need to find the basically the reaction at the supports, like always. That's easy. We can do it easily. So for this beam, symmetric, everything is the same. So it's obvious A is 1 kilonewton and B also is 1 kilonewton. That's the first things. Then the second things, we'd better draw the bending moment and shearing force diagram. That's also easy. We know how to do it. We learned it in previous chapter. Let's do it. So this is, we draw our X and Y axis like that. Okay, this is X and this is Y. This is X, not Y, sorry, X. This is the V diagram and this is the M diagram. So you know how to do it. Let's do it together. So at the beginning, we start from 0. We have a jump of 1 kilonewton, right? And then, oh, we forget, right? We need to break it down to different boundaries. Let's do that first. Let me bring one of my pen here. Okay, so we break it down to the boundaries. So one boundary here and one boundary there and one at the very end. All right, so that's the boundaries. That's good. Then nothing is going on here, so we go all the way down there, right? So it was then 1 kilonewton, right? And then we have 1 kilonewton, so we jump 1 unit down, so we get to 0. Nothing is going on all the way up to like here, and then we go 1 unit down, nothing, and then up. All right? This is what we learned before in lecture 13 or 14, I believe. So, and then the next step is to draw the basically M diagram. To do so, we calculate the area, right? The area here is 1 multiplied by 1. So simply the next point in our diagram here is 1. And then nothing there, so it's going to be then 1. And then we get to 0. And then we connect them by line. If you missed the previous lecture or you haven't studied, please go back and review it again, right? How we draw these diagrams. But it was very, very simple, right? And this is one, basically, kilonewton meter, which is the area of this guy. 1 multiplied by 1 area. Area here is 0. So it means when I'm getting to the new point here, nothing is going to change. From 1, I'm moving to 1 still, and so on. So from this diagram, we can immediately find out the maximum M, the maximum bending, or the bending in the middle here is 1 kilonewton meter. So that's M, that's the first step. The second step is finding the centroid of this cross section, which is very simple. For this shape, we know the cross section immediately where it is. So we are good for that. And then remember the neutral axis. The neutral axis is the one that passing the centroid. All right, so this is our neutral axis. So we call it NA, neutral axis. And then lastly, before we get to the main formula to calculate stress, we need to find I, moment of inertia, which I'm writing it down. I about neutral axis, which we know for a rectangular shape, it is 112, 2 brackets, 1 power 3. Let's use all the units in millimeters. So it's going to be then 150 and 200 power 3. All right. So we need to be consistent. We decide at the beginning, all the length, we keep it in millimeters, and the forces in Newton. So we have I, we have M, we are almost done. We just get to the formula for stresses. So the stress, the bending stress has this formula, My divided by I, all right? Or the negative sign if you want to be consistent. So the stress at C is going to be 0. And we know that. We know that neutral axis, the stress is 0. And also because Y is 0, right? Y, remember, Y was the distance between any layer to this neutral axis. The stress at B, so if I put the formula MYC is going to be M. So M is 1 kilonewton, 1,000 Newton. So it's going to be 10 to power of 6. Remember, this is in Newton millimeter now. And Y, the distance, is going to be 50. And I, we found I somewhere there. Let me write it down again here. 1 over 12, 150, 200 power 3. Whatever number we get, megapascal. And eventually, sigma C, the same story. I is the same. M is the same. Just the distance, which is 100. And as we expected, the stress, sorry, this one is A. As we expected, stress at A at the top is the maximum stress, right? Because the top layer. And if somebody calculates stresses at the bottom, like here, like A prime, he gets the same number, but different sign. It is under tension. And to be, again, if you want to be meticulous and put the sign there, so here M is positive, right? We see M is positive, and our original formula had a negative sign there, so we should put that negative things there, sort of to find out that this is under compression, something negative compression. All right? So as simple as that. If you understand this problem, probably you can solve any other complicated problem in bending stresses. Always I start with a very, very simple problem, but if you can follow it, if you can understand it, The rest of the problems, they all look the same, except they are like more math, more calculation. Instead of a simple rectangular shape, it's a more like T shape, I shape, more complicated cross section, and meaning more calculation. But the steps are exactly the same. All right, so I'm going to stop here to see if there is any question.
So here mx is so in this equation, the stress equation, are we always going to be looking for the maximum m?
Most of
or
the
it depends on the question.
Okay. So Mohammed is asking, always you are looking for the maximum stress, or it is in the question. So it depends. But most of the time, because we are doing the design, we are looking for the maximum stress. And to find the maximum stress, it means we have to find the maximum M, basically. And to find the maximum M, now you remember why at the beginning of this module, we started with bending moment diagram, right? And then when we get to the stress, always we calculate the stress for the top layer or the bottom layer, because we are looking for the stresses. Nobody cares about these middle layers, unless, which you will see in an example, there is a hollow shaft, something that is hollow, or hollow beam, and maybe a crack or something happens in the middle, and we want to figure out what was the stress like inside layer. But again, 99% of the time, we're looking for the maximum stress, right? And in the question, it's going to tell you that what you're looking after.
Thank you.
All right. So I assume that, again, there is silence. I assume that you're good, you understand it, you could follow it. All right. If that's the case, so this simple example, this is important. What I'm going to say is in this simple example, one important thing to notice is that in the middle between this 1 kilonewton and 1 kilonewton, there is no shearing, right? Shearing is 0. And the bending is constant, like pure bending. And it is called pure bending. Pure bending. But why it is important? Because in practice, when we want to calculate the strength of a material in a bending, we just want to simplify things as much as possible. We don't want any other forces or other stresses. We just want pure bending and pure, basically, bending stresses. And that's why in the test setup that people want to test the beam to make sure that it is strong enough, or if they want to calculate these stresses and apply the loads until it breaks to make sure that their calculation is correct, always they use this setup. And this setup is known as a 4-point test. Remember the name? 4-point test. So if somebody asks you, what is a 4-point test? It means you have a beam, you put it on 4 points, the two ends, like this one, and 2 points in the middle. Then you apply the loads until it breaks, right? You calculate these loads, like this 1 kilonewton, maybe for another beam 10 kilonewton. So based on that, you can calculate your M, right? Because based on those loads, and that's it. Then you can find out at which bending it's gonna break, and then the rest of calculation. It's called 4-point test. I have an image here for you guys. So this is a test setup in my workplace. This is actually a large beam. It's, I guess, 4 meters or something. I don't know the exact number right now. But the way that we did the setup here is we sort of fix the middle, like this middle has been fixed here. Somehow you can think of this as a support, all right? And then we apply the load basically downward. So the other side cannot be seen, but it's similar. That's the same concept. Doesn't matter if you put the support in the middle and then apply the load at the two ends, or the opposite way. It doesn't matter if you go up or down. And then I remember when we did this test, we with other guys, we bet that if where it's gonna break, and then we bet for something, and then we decided that this, you see this middle section there, over here. We said it's gonna break over there, and let's see what happens. So if I can play it, you guys can see this video. Please let me know if you cannot. So we were wrong, right? Let me get. So you saw this beam actually breaks in the middle, right? But it's not exactly in middle because the crack later we saw started somewhere around there, all right? You guys, did you guys see the video? It was played well over Zoom?
Yeah, it was good.
Good, okay. So then if that was good, let me show you another test. So this is sort of test that I do. So the background noise is for cutting, it's not for this test. Oops, this one breaks differently. And the reason is because it's wood, and wood is a little bit different because it's not a homogeneous material. It's like it has cracks, it has knots. As you can see on this wood, it has knots. And I have another example to show. Oops, what happened to that? Let's see it again. I'm guessing Emily missed this one. Probably she was checking her text. Luckily, I was on the others, like on this side, like in front of computer. Otherwise, and now it was somebody else teaching you guys Mech 260. So, any question for this test? Are we good?
So the failing pattern, like why there's three different failing patterns here?
That's a good question, Mohammed. Yeah. It was different between these three because wood, unlike other materials, it's not a homogeneous material. Its property is not the same at all the points. That's what it makes it more complicated. It has knots, it has cracks, and sometimes a portion of a wood is like more humid, like the moisture is more. Some portion has been dried, or maybe for a tree, like an insect, basically eating a portion of the tree, and there is a hollow portion, maybe even a micro hollow. It makes it weaker at those areas. That's why we saw a different pattern. But the same test, if we do it for a steel, aluminum, copper, like this material, which we call them like homogeneous, meaning the same material at all points, they're going to break the exact same patterns. But if the same, like even with metals, if you test something that has been cast, then probably we see a different pattern. Okay. All right. So if there is no other question, then let's solve one serious problem together. And example 2 is a little bit more complicated, but let's see how we can solve it. I'll let you guys to read it and then think about it for 30 seconds, and then we get start, and then we try to solve it. I'll do the same. Okay, so we have a cantilever beam, and the cross section is T-shape. And then there is only one M, pure bending, M. We know M, kilopascal inch, kilopound inch. And we have all the dimension that we want, and we just want to calculate the maximum stress, right? Since we have only one M, and this M is constant at any intersection, then M is just these numbers. So it makes our calculation easier. First step, we need to find out the centroid. You know how to do it. I guess centroid is a point over there. So if that's the case, then this is going to be my neutral axis. All right, so this is going to be the neutral axis. All right, and you know how to find this neutral axis. You break down this area to like the one at the top and the one at the bottom. I'm not going to repeat the calculation for that because you can simply find the neutral axis. If you forget again, go back to module 4. It's going to be 5 inches. So that's the neutral axis. We found that one. And then the next step, we calculate I, moment of inertia. I'm writing down here, I. So we have two areas. We have area 1, and then we have area 2. And remember, we said to calculate moment of inertia, we need to transfer the axis, right? And again, if you forget this topic, or if you missed the lecture, please go back and study that carefully, because if you make a mistake, like in the first step, all of your calculation is going to be wrong. So area 1, we know the center. Area 2, also we know the center. And also we know the formula for moment of inertia for each of them. For area 1, I1. And we said we put a bar there so we don't forget that it is at the center. Centroid of that area, 112, 2 brackets, one of them power 3, which is 2 here. And the same here, I bar 2, 112, 2 brackets, 2, 6, 3. So that's about moment of inertia. And then we cannot just simply add them. We need to transfer these things there, and we need to transfer these things there, and then we can add them, right? And we know the distance. So then I about neutral axis is going to be I bar 1 plus the area, 6 multiplied by 2 multiplied by the distance, which the distance is 2 to power 2. This is for the first area, plus I bar 2, which we have the value, plus area, again, 6 multiplied by 2, and the distance, which is 2 again. This distance is 2 inches, this distance is 2 inches, right? And this is power 2. So that's I, and then simply sigma is M Y I, right? So sigma is MYI, and don't forget for the axis that we selected, right? This is, if this is the neutral axis. Let me extend it a little bit so we know where we are. Okay, so in other words, this is our x-axis. This guy is y, and then the z-axis is coming down like this one. So this is y, and this is x. So this is then x, y, y, and this is z, right? The first picture that I showed you. So sigma is my. We have I, we have m, and don't forget m here at the top. It is 8,000 pound inch. All right. So what about y? So we know the top portion is under tension and the bottom is under compression. How we know that? So try to visualize if this beam is going to be bent, right? If you apply this M downward, it's going to bend down. So probably top portion, most likely the top portion is under tension and the bottom is under compression. So for me to calculate it, I say sigma tension, then it's going to be M. Let's put the values there. It's going to be 8,000. And what about y? Y is here is the distance from the top layer, right, on the cross section to the neutral axis, which is 3 inches, divided by I. Don't forget this one, the distance between top to neutral axis. All right. And if you want to follow the signs correctly, so you should put basically a negative sign in the formula there. And this M also is clockwise, and clockwise we consider it negative. Oh, we have another negative there. And the result is going to be a positive number, PSI. And also we know it before even looking at the signs. And sigma compression, same things. I, we have a negative things there. And then we have 8,000 there. And what is the distance or the y from the bottom to neutral axis? It's -5, right? So it's going to give us minus something PSI. All right? Very simple, right? It's just a tedious process. You have to first find the centroid, which is easy. You just need to break down the area to different areas and then the rest. Then the next step is to basically find maximum M, which in this example, M is the same at all the cross section. We don't need to worry about it. And M is 8,000 pound inch. And then I, we need to find I. We know how to do that. And then the rest, we just use the formula that we have. If we cannot realize the positive or negative, the tension and compression, then we'd better follow this sign. There is a negative sign there. We put the value for y based on the things that we see, like top portion is positive, bottom is negative, and so on. Okay, any question for this one?
So I think in the previous example, we didn't use the negative sign in the equation, right? Like I'm just not following.
So this one, we
did? Okay, I guess
yeah,
I guess I'm not the one following. Okay, thank you.
Did the negative things here?
Yeah.
Right? And M was positive. On this graph, M is positive. So, and also, if you don't like to follow these signs, but you need to have a good visualization, you tell yourself that, okay, this beam probably, if it's going to bend, it's going to bend to something like that if you exaggerate, right? And then our feeling tells us that sort of the top portion has to be under compression, right? Remember this beam that I have, if I bend it like that, so it is intuitive to think that the bottom is going to be under tension. But at the same time, for more complex beam, we can follow these signs, and we need to be careful for this Y. Always Y the vertical axis, right? The origin start at the centroid, like this one, and we need to put like y its sign there, which is y for point B and A, they are positive, but for point A prime, it's negative. All right, so time is up. We're gonna come back after break to solve this example, but let's all of us for 1 minute take a look at this one. So during the break, maybe we can think about it, and then after break, I'll solve it. So it is a simple beam, but the cross section is a pipe, right? This beam is a pipe. So the cross section is a hollow shaft, basically, or circular, maybe cross section, you can call it. And we apply two loads, and these two loads, they are different, 1,000 and 2,000. So unlike this example that we solved, which the load was equal and then M was constant, we need to be careful. In this example, these two loads, they are not the same. So we need to carefully draw the bending diagram and make sure what is the maximum bending, because the question asks us to find the stress at the maximum point, right? We want to find out the maximum bending stress, right? At which point we want to calculate stress like point A and point B, which is inside this pipe. Good. All right. We'll come back in 30 minutes. Bye for now.